The whole point of trigonometry is to convert between angles like this in a triangle and the sides that make it up. And typically we're talking about right triangles, although that's not always the case. That's what we're going to start with here, though, because that's easier to think about. We already know how to describe certain coordinates of the triangle. For example, right here, this would be just the x coordinate, which is 6, comma 0. But in this, right here, obviously this is the origin, and up here would be 6, comma 3 in this case. So we already know how to describe the different points of the triangle just with normal analytic geometry. But we want to come up with a way that we can relate these different coordinates and the points to this angle itself from this origin. And trigonometry gives us a way to do that. And the way we can think about this is by understanding what each side of the triangle represents. So each side of this triangle, based on the geometry, represents something very interesting in terms of the coordinates. So for example, right here, the hypotenuse of the triangle, the longest side, represents the distance between the top right corner 6 comma 3 and the origin. And we already know how to take the distance between 2 points on the xy plane. This side down here, which we usually call the adjacent side because adjacent means touching or next to, and this is the side that's next to this angle here. Obviously, the hypotenuse is also next to that angle, but that already has a different name. So the adjacent side is the side that touches this angle that we're talking about, theta, but is not the hypotenuse. The hypotenuse will always touch the angle theta. But this adjacent side right here also represents something interesting. It basically represents the x coordinate, if you think about it. The length of this side, which is 6, happens to be the x coordinate for this point on the top right. And this side right here, we call this the opposite side because it's across from the angle theta and it's not touching it at all, unlike the other two sides. This side is the y coordinate. And you can see that because the length of this side will be 3, which is the y coordinate of this point up here. So each of these sides, just from a purely geometrical perspective, also means something specific when we graph a triangle, a right triangle on the xy plane. Before we started with trigonometry, there was really no way to do this. We could work with the coordinates of the different points of a triangle, but we had no way to convert from an angle like this to the different sides of the triangle. But trigonometry gives us a way to do that. But before we get into that, let me explain one of the problems that comes along with geometry. The entire thing that we're trying to do here is come up with some function, which we'll later learn are called trigonometric functions, that take in an angle theta that could be measured in degrees or radians. So for example, this angle theta down here could be like 30 degrees, 45 degrees, 60 degrees, whatever. It takes that in as an input and then it outputs one of the side lengths. So in this example, I want to output the adjacent side. But the problem here, as you can see, is that there's actually an infinite number of right triangles that could all share that angle theta, but have different side lengths. And the reason for that, if you think about it, is because of similarity. So each one of these triangles here, the pink, green, and orange one, are similar to one another. The reason they're similar, if you want to get into the specifics, it's due to AA similarity from geometry, angle-angle similarity. So they all share this side right here, theta, and they all have a 90-degree angle at the bottom right corner of them, of each triangle. So they share two angles, which means this other angle up top here has to be the same between each of them. And that's actually the definition of similarity. If all the angles are the same, then the triangles are similar. But what that means is that they each have a different length for their adjacent side. And it's not only this three that we're talking about. It could be any number of them. So the way that I drew it here, the green one is really a scaled version of the pink one. It's twice as large as the pink one in both of its coordinates. And then the orange one here is 3 times as large as the pink one. But you could have 2 or 3 or 4 or anything in between. It could be 100 times larger. There's actually an infinite number of them. So if we try to come up with a function like this that takes in an angle theta and gives out the length of our adjacent side, you see that we're going to run into problems. So for this first triangle, the pink one, you see that the adjacent side there would be 2. For the green one, you see that the adjacent side here would be 4. And then for the orange one, you see that the adjacent side here would be 6. So whatever function we come up with, we put in one angle theta, and we get actually an infinite number of possible outputs, which is bad because obviously with a function, for every input, you should have only one output. So that's a serious problem, actually. We're going to need to come up with some way to solve that. How can we Even though with this angle, we can have an infinite number of right triangles having that angle in the xy plane, how could we come up with a function that comes up with one specific number for each right triangle? That's the question we're asking ourselves. And the answer to that problem is that instead of trying to output a side length from our function, we're going to instead output a ratio of side lengths. That's the key. And the reason this works is because of the definition of similarity. If you have two triangles that really are similar, like say the pink one and the green one, then if you take the ratio of any two sides in the pink one, that will be the same number as the ratio of the same two sides in the green one, even though the green ones are twice as large. But because it's twice as large in the numerator and the denominator, that will cancel out and you'll get the same ratio between them. That's the whole point of similarity, actually. So if we can intelligently use that technique to assign one single number to a specific angle for our function, even though there's an infinite number of similar right triangles that could be represented with that angle. And that's the trick. So if we actually work this out, if you see here, for example, I'm assuming that we want to come up with some function that spits out the opposite over the adjacent angle or sides for a given angle theta. And if we test that out with the different right triangles, you can see that we'll get the same thing. So in this case, the opposite of the pink triangle is 1. The adjacent side is 2. So 1 over 2 is 1/2. For the green triangle here, then the opposite side has length 2. The adjacent side has length 4. So we'll get 2 over 4. And then for the orange one, the opposite side has length 3. The adjacent side has length 6. So we get 3 over 6. Now, all of these numbers are the same. So all of these numbers are actually the same ratio. They're all 1/2. So that works. That solves our problem. Now, for any particular value of theta, whatever it is, even though we have an infinite number of right triangles that have that angle of theta that we could use as a model for our angle theta, we're going to get exactly one number out. And that's the trick. Now we can actually talk about a function because we don't get we don't get an infinite number of outputs for one input. So after you understand that, the next logical question is, if our trigonometric functions have to have outputs that are the ratio of side lengths rather than the side lengths themselves, then how many total possibilities are there? And if you think about this for a while and you're clever, you might realize that this is actually a permutations problem. So for example, one way that we can think about it is we can think about the numerator and denominator here as the two spots that we have to fill. So this would be like our spots, if you're thinking through the permutations kind of terminology. And we usually call that R. And then the number of sides here, so hypotenuse, opposite, and then adjacent, the three possible sides, those would be like our options, which we would call N. And if you think about it, we have N total options, 3 total options, and we're trying to use those 3 options to fit them into 2 total spots. So what this problem really becomes is it becomes a permutation problem. It becomes 3, choose 2. And we know how to calculate this with the permutations logic that we've talked about in another video. And by the way, the reason that it is permutations instead of combinations, the reason is because if you swap the numerator in the denominator, then you get a different ratio. So in other words, the order does matter. The numerator has to come first, and then you divide by the denominator. If you didn't have that, then it would be combinations. So after you understand that, then we want to actually calculate that. Now, I won't go over why exactly this formula makes sense. We've already done that in another video, but if we just use the formula, so 3 permutations 2 here, then when we solve that, we'd get 6. So in other words, according to our permutation formula in our logic, there should be 6 trig functions, 6 possible ways that we can form a ratio between 3 sides that are unique. Now, the problem with permutations and combinations is that the formulas don't tell you what the options actually are. They only tell you how many total there are. But that's still useful because it means that after we actually come up with 6 unique ones through guessing and checking, then we can stop. We don't have to keep trying options that don't exist because we know exactly how many total there are. So what I'm going to do here is just think about the different possibilities in no particular order. So one thing we could do, so if we have hypotenuse over here, then we could start with hypotenuse in the numerator, and then we could do the opposite in the denominator. That's one option. And then we could keep hypotenuse in the numerator and do adjacent in the denominator, so hypotenuse over adjacent. And the reason you could also do hypotenuse over hypotenuse if you wanted, but that's not interesting because that would just always be 1 if you have the same number in the numerator and denominator. That's why we're excluding them here. So that's one possibility. I would say the next possibility is let's basically do the same thing, but now let's keep the opposite in the numerator. So let's keep the opposite in the numerator and then change the denominator. So opposite over hypotenuse and then opposite over adjacent. And then finally, let's do that with the last one. So adjacent is now going to be, we're going to hold that in the numerator, and then we'll vary the denominator. So adjacent over hypotenuse and adjacent over opposite. So that's it. These should be our 6 trig functions, that the 6 possible ways that we can represent a ratio given 3 sides in a triangle. And now we want to name these. Now that we have all these 6 possibilities listed out, we want to name each of these functions. And by the way, I have rearranged these because they are presented in a very specific way normally in a trigonometry class. So the first one here, opposite over hypotenuse, we call that sine. So sine, and then the input is always theta. And I'm also going to mention how we pronounce that. So that's going to be sine. It's pronounced like that. For the second one, adjacent over hypotenuse, we call that cosine. And then it's pronounced like this, cosine. This last one, or this one down here, opposite over adjacent, is tangent, which we pronounce tangent. And you might have worked with tangent lines before in geometry, if you're doing geometry before trigonometry, which is typical. And then over here, this one we call cosecant. CSC is the abbreviation, and that basically, we pronounce that cosecant. And these names probably don't make sense, but I'll explain them in a bit, or in later videos in more depth. This one is called secant, S-E-C, so that's secant. And then this one down here is called cotangent, which we represent with COT. Cotangent. Now, these names might seem arbitrary, and some of them are. So some of them are historical accidents. Some of them are sort of logical. We're not going to get into that during this video, but these are what the main trig functions are that you go over in a normal trigonometry class. And throughout the next few videos, we're going to go much more in depth on what they mean, what they represent, and why we should care about them. Thank you.